Welcome back. This is our fourth lecture on Matroids. At this point, we've seen the basic definition, we've seen examples, we've seen characterizations, and also importantly, and perhaps the most important characterization we've seen is with respect to the greedy algorithm. We saw that the greedy algorithm succeeds in finding a maximum weight base of a Matroid for any weight vector. And that's a characterization of a Matroid. We're now turning our attention to polyhedral theory. We're going to make use of everything that we've seen so far, but in particular, we're going to characterize first the polytope of independent sets. So for M a Matroid on a ground set E and independent system I, the polytope of its independent sets, which I'll denote like this, but also when there's no ambiguity, just for shorthand, I'll write P to denote it. This is the convex hull, as usual, so we've usually done in this set of lectures, of all incidence vectors of independent sets. So in other words, I is an element of I. And the main result we're going to show is that this is equal to the following relaxation. I'll use very similar notation to what we've been using. Again, for shorthand, I'll call this Q. So this is all vectors that are non-negative, and also x of u, which again is the sum over all elements of u of xi, is upper bounded by the rank with respect to the Matroid of u. And this is true for, this has to hold for every subset u of the ground set. So again, this is an example of a polytope that has exponentially many facets. And the main result is that Q is equal to P. And we can note that one inclusion is essentially immediate. Indeed, if you take the incidence vector of any independent set, well then it's going to be non-negative. Its elements are 0 or 1. And also, what would x of u be? X of u, in that case, would count the cardinality of u intersect with our independent set I, and that is certainly going to be upper bounded by the rank function of, by the rank of all of u. So we're going to turn our attention now to the reverse inclusion, which is the interesting direction, and we're going to show this reverse inclusion by demonstrating that the system is totally dual integral. And we're going to do this by writing down the maximum weight problem. This will allow us to leverage our results on the greedy algorithm, which essentially characterizes what an optimal solution will look like, and then looking at its dual. Okay, so let's take this one at a time. Again, we will prove the theorem through the reverse inclusion. We're going to prove the reverse inclusion by showing that the system is TDI, total dual integral. And how do we do this? We need to show that for any weight vector, and here of course is just the cardinality of the ground set E, I need to show that the dual not only has an integral value, but also has an optimal solution, which is itself integral. And so let's write down the optimization problems. The primal is a maximization of W transpose X, subject to the constraints that we wrote down for Q. So X of U, which as mentioned is just the sum of Xi for every I in U, is upper bounded by the rank of the set U. This has to hold for any U that's a subset of the ground set, and also non-negativity of the variables. So this has cardinality of E, or n in our notation here, variables, and an exponential number of constraints. And so the dual will have the opposite. It's going to be a minimization over the sum over all subsets U of my dual variables yu times what we get from the right-hand side, r m of u. And now we have one constraint for every element of E. And our constraints are going to be the sum over all u such that I is an element of u. The sum of yu should be at least equal to the weight vector wi. And we have one of these constraints for every element of the ground set E. And then also we have non-negativity for every u. It's pretty straightforward to see that we can assume without loss of generality that the weight vector is non-negative. Now remember that for total dual integrality, we need to show that we can find that the dual has an integral optimal solution for any integral vector w. But you can check easily that it's almost immediate by looking at the dual, but you can also see from the primal that we can take w to be non-negative. I'll just leave this as an exercise. Show that we can take w to be a non-negative integral vector without any loss of generality. Okay, now let's continue and move on to the proof. So first of all, we're going to take advantage of the greedy algorithm. So in the spirit of the greedy algorithm, let's order the elements of the ground set so that the weights are non-increasing. In other words, we order them so that W1 is bigger than W2, is bigger than W3, etc. Wn is the last one. And we're assuming that these are non-negative. So this is greater than or equal to 0. Since we have this ordering, let's let ui be the elements 1, 2, up to I in this ordering. In other words, the ordering specified by the weight function. And now let's take I to be all the elements I such that the rank of ui equals the rank of ui minus 1 plus 1. Note that what we've done is we've exactly defined the solution of the output of the greedy algorithm. So let me write that clearly here. So note that I is the output of the greedy algorithm, which is to say that I is a max weight independent set, which means that it is an optimal solution to the primal. So in other words, I is a maximum weight independent set, and hence x is equal to its incidence vector is a primal optimal solution. Now let's go on and show that the dual has an integral optimal solution as well. So now let's define a dual solution. And we're going to do it in the following way. Now what is the weight of this set I that we identified? Well, again, the definition of this is the sum over all I in the set I of wi. And just by virtue of how we defined it, this is the sum over all I from 1 to n. In other words, the sum over all elements of wi. But let's flip back and see which ones I chose. So I here is just the elements I where r of ui is strictly bigger than r of ui minus 1 by 1. So that means that I could just write, I could put here r of ui minus r of ui minus 1. And you see that when I got to put I in my set capital I, then this coefficient here is equal to 1, otherwise it's 0, and so it's not counted. So this is indeed exactly correct. Now what is this? In turn, we can write that this is equal to Wn times the rank of Un plus the sum of Wi minus Wi plus 1. This is non-negative because the weights are organized in decreasing order, times r of ui. In other words, this is equal to the sum from I equals 1 to n of non-negative weights lambda I times r of ui, where I've just taken lambda I to be equal to wi minus wi plus 1, and lambda n is equal to wn. Okay, so from this is essentially my dual variable. I'm going to define y in the following way. Let's let y, I need to define y of u for every subset u. And when the subset u happens to coincide when one of the n nested subsets, then it's going to equal the value lambda I, and otherwise it's going to be 0. So in other words, the support of y is on those nested subsets. So it's straightforward to check at this point that y is dual feasible, and also just by virtue of this sequence of equalities that we've written at the top of the page, not only is it dual feasible, but also the sum of yu r of u is exactly wi. In other words, we've found a dual feasible variable and a primal feasible variable, and their values, their respective values in the primal and dual are equal. Hence, they are both feasible. So let's note it down in particular that this is optimal, and let's see what we've learned from here. So we conclude first that the primal and dual are always have integral optimal solutions. Let's write that down. Primal and dual have integral optimal solutions. And this is what we need for TDI. It's also interesting for us to observe something about the structure here, because it should remind us of some things that we've already seen in previous lectures. Note that the dual, we can always take the dual solution to have support on a laminar set. In particular, in this case, it's actually nested. So let me just note that down. The dual has an optimal solution whose support is laminar. Again, in this particular instance, it's nested. Okay, now let's turn to the base polytope. Again, we've seen this kind of thinking before when we were talking about the matching polytope and then perfect matching polytope. This is somewhat similar. As a corollary, we're going to characterize the convex hull of all bases of a matroid. And let's denote that by the polytope P base of M. Now I'll keep track, at the very least, of the subscript so we don't confuse it with P. Again, by definition, this is the convex hull of all incidence vectors where B is a base. In other words, a maximal independent set. And Q base, or Q base of M, sometimes I'll drop that, is going to be the set of non-negative vectors where x of u is less than rm of u. This is exactly what we had before so far. For every u, that's a subset of my ground set. But now I also ask that x of e is equal to the rank of the ground set. So let's prove that these two are equal. I guess I should say, what is the corollary of the statement? The corollary says that for P base and Q base defined in this way, P base is equal to this relaxation. Again, a relaxation that has exponentially many facets. So let's give the proof. It's actually pretty straightforward given what we've already shown. So the fact that this is a subset of Q is again very straightforward to verify, and then again equally straightforward to verify that this is a subscript of the independent set polytope of M. So this is what we've got so far, and we know from our previous work in this lecture that this is equal to Q of the independent set, and we're going to be using this. All right, so now let's take an element in Q. Well, just from this set of inclusions, we know that this means that X is in the independent set polytope, which means that I can write it as a convex hull of incidence vectors of some independent sets. So I'll just write this as a sum over all independent sets. Not all the alpha i's need to be positive, but we do know that the alpha i's are non-negative and sum to 1. So sum of alpha I is equal to 1, and the alpha I are non-negative. They're defining a convex hull. Okay, now let's look at X of E. X of E is equal to the sum over all elements, I equals 1 to n, of xi. And I can write this in the following way. This is the sum over all independent sets of the sum over I in I of the weight alpha I, which again is exactly equal to the sum over all my independent sets of the weight alpha I times the cardinality of that independent set I. So now looking at this, you recognize that this is, because this is an independent set, this is equal to the sum of alpha I times the rank in M of I. And certainly the rank of any independent set is less than or equal to the rank of the entire ground set, since the rank of the entire ground set is the size of a base. This is less than or equal to the sum of alpha I times the rank of E. But the rank of E now no longer has, I can bring it outside the summation, and because the sum of the alpha i's is equal to 1, this is in turn equal to the rank of E. But since x of E is equal to the rank of E, that's the constraint, one of the constraints in Q, then we know that we must have equality throughout, and in particular, we must have equality at the only place where I had written an inequality sign, which is right there. And therefore, this means that R of I equals R of E for all I such that alpha I is positive, which is another way to say that this decomposition we have of X is not just a decomposition in terms of independent sets, but it's a decomposition in terms of bases. Each I such that alpha I is positive is a base. And that is exactly what we needed to show. And this gives us now a characterization of the base polytope and the independent set polytope. We'll pick this up next time.